Okay, so basically I just wanted to present some of the work I've done recently together with some collaborators from Imperial, in particular Katrina Lithgow. And the idea was to develop a within and between host model. So many people talk about integrating the two scales, and I just tried to give it a go, really. In particular, I'd like to apply that to the case of HIV. So I'll talk about HIV for a bit, but any question about HIV should be referred to Deirdre, that has been just volunteered now, or anyone who knows something about HIV. And I would like to discuss the fact that HIV is undergoing two conflicting types of evolutionary pressure. And I'll describe the model construction. I would like to spend quite a bit of time on the model and for once go through the details of the model and present also something about the results. So I'll talk about the between host model and the within host model. So HIV is a retrovirus, which as far as my understanding goes, means it mutates a lot. And it's transmitted via blood transfusion, sexual contact, and breastfeeding. Originally discovered in 1981 in the States, but it seems to have come from primates in Africa and moved to human in the 20th century. And I would like to remind people that it is an ongoing pandemic, despite being a lot slower than the flu pandemic. And it's in general very difficult to model. So I promised to myself not to have anything to do with HIV, also from a modeling point of view. But it's in general very difficult to model because most of our mathematical models assume that the environment remains constant during the epidemic, or at least during the duration of the infectious period. And this is definitely not the case for HIV, where the infectious period lasts for years or decades. So the particular infectivity profile of HIV is a bit weird, and there has been quite a lot of work done on this from Deirdre and other people. So it's a bit more complex than that, but this is a good simplified representation with 3 stages. So we have an acute stage early on with a very high infectivity, then what is called the asymptomatic stage, which lasts for very long and has a reasonably low infectivity, and then you have the AIDS stage. And then there is, one might include a tiny bit where the individual is not infectious anymore, but has not died yet. By set point viral load, which is a quantity that will be used quite a lot in this talk, by set point viral load, I mean the roughly stable level of viral load during this period, and so during the asymptomatic stage. And this level of viral load is measured in log 10 viral copies per milliliter of blood. So the set point viral load is an important quantity because, although imperfect, it kind of predicts infectiousness. So it varies a lot between individuals. So this is roughly stable in an individual, but between individuals it changes quite a lot, by really orders of magnitude. And so if you have here on the x-axis the viral load, then it seems that individuals with a larger viral load transmit more, which is kind of reasonable, but also individuals with a very high viral load have a very, very short duration of this stage here and very rapidly progress to AIDS. So viral load also predicts how fast you're going to move to AIDS and therefore how short your life is. So by transmission potential, I mean the overall infectivity that is spread during your infectious period, which is the area under this infectivity profile. And some individuals have a very low infectivity here, but they are in that stage for very long, and some individuals have a high infectivity, but they are there for a limited amount of time. And so if you take the product of these two curves, you get something like this, where the individuals with the highest transmission potential are those that have an intermediate set point viral load. And set point viral load seems to be heritable in the sense that an individual with a high viral load seems to infect other individuals and give them a high set point viral load. Although the data is really sparse, it's always very difficult to understand these things, but this is what data seems to be suggesting. And it has been steadily increasing for the past 20 years, but now it seems to have plateaued. So if you look only at the black curve, this would be the distribution of set point viral load seen in the population, I guess. And it seems that the mean value is close to the value that can be theoretically calculated by multiplying these two curves, and which would be the one that maximizes the transmission potential. So this might suggest that a set point viral load has evolved in the population in order to maximize its transmission potential. Now I jump into the within host framework. And within host we have many different strains that can be distinguished, for example, in terms of replicative capacity. So the replicative capacity would be the rate at which a strain reproduces within the host. So it's basically its fitness within the host. And it seems also from data that infection with a strain with a high replicative capacity leads to a higher set point viral load. Mutation occurs very fast. There is a doubling time of a day. There is a per base mutation probability, which has been estimated being that quantity there. And the infection lasts for very long, so there is ample room for strain competition, and the strain competition should favor the strains with the highest replicative capacity because they take over within the host. And because of what I said here, they also seem to be the most virulent ones, which give you a high set point viral load and a low duration of asymptomatic stage.
Question?
Yeah.
Is replicative capacity, is it like a little r, an exponential growth coefficient, or what is it?
Yes. This is how I would interpret it,
Okay.
at least in this talk. But maybe somebody has some comments on it?
It's just measured differently in different experiments. Often it's measured as in competition assays, so which one wins out, which is not necessarily just little r.
Okay. So there are these two conflicting evolutionary pressures. So there is a within-host competition that tends to favor strains with the highest replicative capacity, and in fact there is experimental evidence that shows that the average replicative capacity within a host seems to be increasing over time during the infectious life, and then there is a between-host competition that tends to favor instead the strains with the highest transmission potential, and indeed. It seems that the distribution of set point viral load has converged to achieve its maximum at the population level. So these two types of evolution are quite different because this is what we will call short-sighted evolution, because the strain that is fittest at reproducing within the host tends to lead to a high set point viral load, which is not the optimal at the population level. Okay? So we just decided to just give it a go and see what happens if you model both scales at the same time. So the between-host model, I just simply wanted to use multi-type epidemic models because there's a rich theory developed by, summarized in the book by Diekman and Heisterbeek. But I had to go through the assumptions to see if they are really plausible. So the theory is based on the assumption that the system is autonomous. So as soon as you get infected, the behavior of your infectious life is independent of what happens outside. Which is not true, because there is evidence of superinfection with HIV, which means that what happens within you depends on further infections that you get from outside. Then the infectious life of an individual is very long, so there are control policies in place, behavior change, and so on. Distinguish individual in types, that would be okay, because the set point viral load seems to be predicting infectivity and duration quite well, so we can assume that types are individuals with different set point viral load. And we need to describe the rates at which each type infects every other type. And this is not really well known, but there seems to be some heritability. So the assumptions I make is that the system is autonomous, which I've just said is not true, but I just ignore superinfection that is shown to exist, but we don't really know how this impacted dynamics, so I just don't include it in the model, also because it's really tough. And I distinguish individuals in types based on the difference in their set point viral load. And I assume that the infection is caused by a single virion entering an individual, and that virion will determine your set point viral load, because infections with high replicative capacity tend to lead to higher viral load. And so I define the type I of an individual as being infected with strain I at the beginning. And all susceptibles are identical. The transmission will depend on the within-host competition, because a strain will mutate into different strains, and this will decide which strain you are transmitting to the next host. It's an SI model with demography, homogeneous mixing, and I use a deterministic model as a start. Is always a good idea. I think. So the system dynamics are constructed in this way. An individual of type J lives for a duration Tj, which is the sum of the duration of all the 3 stages. And it transmits strain I at a rate given by a infectivity profile from individual J to individual I at time tau since the time of the infection of the individual. And the transmission will be successful if it hits an individual in the susceptible fraction of the population, which changes over time. I use I of t, sorry about the notation, to denote the incidence, not the prevalence, the incidence of individuals of type I at time t. And so the equations are like this. New cases of type I are generated because the infectivity profile that leads to the creation of new individuals of type I from an individual of type J at time tau is multiplied by individuals that got infected, individuals of type J that got infected tau units of time ago. Then I integrate over all times between 0 and the duration of the life of an individual of type J, and then I sum over all types J. Okay, this is the overall basically infection pressure that would create individuals of type I, and that needs to be multiplied by the fraction of the susceptible population. The susceptible population is given by the total population minus the prevalence. And the prevalence is the integral of the incidence over time and then summed over all types. Clear up to now? Any question?
Why is S of t not inside the interval?
Because it does not depend on the time since infection. Because the integral is over the time since infection of an individual. An individual of type J infected tau units of time ago now will have age tau, and its infectivity that would generate individuals type I is given by this function as a function of time since infection, and t is not, this integral is not over t. Okay? So I'll leave the system here for you to have a look at it. But this system like this have been studied quite a lot, and it's quite easy to construct the equilibrium straight away. So if I use a star to denote the quantities at equilibrium, then the incidence of type J at any time is a constant, ij star. So it comes out of the integral. I remain with the integral of this infectivity profile. And the integral of infectivity profile ij is what I call kij, and is one of the elements of the next generation matrix, because that is the overall infectivity from type J to type I. And I remain basically with this equation where S also is at equilibrium.
What's that? Is to infinity not like 2i or something?
So this one here.
Yeah.
So this an individual of type J lives for a duration Tj, and then it's dead. You can also think of beta ij of tau being a certain shape that is 0 after that point. And because the Tj differ from various individuals, I just put infinity here. Okay. Yeah. So the general theory says, so this is K is the next generation matrix, and the general theory says that if K is positively regular, so it's non-negative in general because all the elements are the total infectivity from one type to another type, so they are all non-negative. And if we assume that different types mix in the population, in the sense that it's not possible that if you have an epidemic over a certain set of types, then other types are not affected by the epidemic at all, then the matrix is called irreducible. And under these assumptions, the theory says that K has one real positive dominant eigenvalue, which is what we call R0, and the associated eigenvector V, which I'll call the dominant eigenvector, has all elements of the same sign. And so R0 represents the per generation multiplicative factor, and V gives the stable proportions of individuals of each type during a generation. Okay? So I can go through how next generation matrices work with a simple example if you want me to, but okay. So assume this is the next generation matrix. So assume two types, for example, adults and children. So an adult is of type 1. An adult in a generation infects another adult. A child infects 2 adults. An adult infects 3 children, and a child infects 4 children, okay, in a generation. So this is a really toy example. The incidence, so the number of cases in each generation for the moment is, we have 1 adult and no children. So in total we have, the total number of cases in generation 0 is 1, and that guy is an adult. The proportions of each type is 1 and 0. The number of cases in generation 1 will be constructed in this way. So I take the matrix K and I multiply by the vector in generation 0. So 1 adult generates 1 adult and 3 children, and 0 children infect nobody. So now I have, in the next generation, I have 1 adult and 3 children, total number of 4 cases in proportions 1/4 and 3/4. Okay? The second generation is given by the same matrix multiplied by the vector of generation 1, and now I have 7 adults and 15 children. So the 4 cases that I had before now become 22 cases. So I multiplied by the total number of cases by 5.5 this time, and the proportions have changed to these proportions here. If I keep on doing that, then the per generation multiplicative factor tends to converge to a certain value, which is 5.37 in this example, roughly, and the proportions tend to converge to these stable proportions. So this per generation multiplicative factor is the dominant eigenvalue of the matrix, and it's R0, and these proportions are the elements of the dominant eigenvector. So what I'm trying to say is that a typical individual, after this convergence has occurred, a typical individual is for 31% an adult and 69% a child, and a typical individual will reproduce and generate 5.37 typical individuals with exactly the same characteristics. Okay, so this is how the next generation matrix work. So from what I said, from the system at equilibrium, I can calculate R0 as the dominant eigenvalue of the matrix, and the incidence of all types are the elements of the dominant eigenvector. So here, these are the elements of a vector that get multiplied by the next generation matrix, and because of the property of an eigenvalue of a matrix, this vector times the matrix gives the vector itself multiplied by R0. So this product here is R0 times the vector itself. That needs to be equal to the vector itself. So it means that this fraction here has to be 1 over R0 to cancel out the factor R0 in front of it. And so I get that the fraction of susceptible population is 1 over R0, which is the standard result for the standard condition for equilibrium. The recipe basically works like this. I calculate K. If I have the beta ij of tau, I have to integrate that function over time. And each of them gives me the elements of K. So I have the matrix. I calculate the dominant eigenvalue. I calculate the susceptible population as n over R0. And then I have to find the dominant eigenvector of K, which is easy to do with a computer. In this case, I found it such that the sum of all the elements is 1. Then the incidence will be proportional to this vector here, to this dominant eigenvector, with a constant in front of it, which is the total incidence. And I calculate that constant using the total prevalence. So the total population minus the susceptible gives the total prevalence. And the total prevalence is the incidence of every type multiplied by the duration during which they are infected. And so from this equation, I basically find I star and I reconstruct everything else in the model.
Lorenzo,
Yes?
any assumptions about the population size of each type?
No. You don't need any assumption for that.
Well,
No,
Which is to say
okay.
it's determined by the virus, not the population.
No.
It's infinite for all types. otherwise.
Yeah, no, there is a little issue here. So there are different types of multi-type models. So in certain types, an individual has a type irrespective of the fact that it's infected or not. For example, has an age, belongs to an age class. So susceptible individuals have a type already. In this model, the susceptibles are all equal, and they are assigned a type at the point of infection. Okay?
Replenish somehow the susceptibles.
Excuse me?
The susceptibles replenish somehow.
In this model, because I assume n constant, it means that if somebody dies, becomes susceptible again. So yeah, but this assumption is not particularly realistic, and therefore I move from that system to a more complicated system, where n is a variable. So this is the old system. In the new system, n changes over time, because individuals can die, and I have a birth rate. So the system is the same as before, but now individuals of infectives of age tau, in order to transmit a strain I, according to this function here, they need to have survived natural death until age tau, which is this factor here. N now is variable. The total number of susceptibles is the n minus the total prevalence. The total prevalence also takes into account how individuals die over time of natural mortality. And then the total population changes because of a total birth rate, a per capita death rate, and here I have, and these are the individuals that die of AIDS at the end of their infectious period. So an individual needs to get infected at a certain point in time, and Ti units of time after the infection, that individual will die, provided it has avoided dying of natural causes during the entire infectious period. Does it make sense? So this is a delay. You know, individuals that die at time t are those that got infected Ti units of time ago. So this is a very simple integral differential equation with delays. And so it's quite difficult to solve and analyze. But you can still simulate from it.
Lorenzo?
Yes?
In the equation for S of t,
Yeah.
picking both models, why you're taking off the incidence, but you've integrated I at t minus tau.
Mm-hmm.
But surely you should integrate with respect, you just would integrate I of t dt to take the instance off, because you need to sum the incidence.
So at time t, the individuals in the prevalence, the individuals that are infectious at time t, are those that got infected.
Now I see incidence.
Here.
Yeah.
Yeah, so the susceptible population is the total population minus the prevalence. So this big term here is the prevalence. Okay?
But people are joining the prevalence all the time.
Yes, people are joining because they get infected, and this is accounted in the incidence. But at a certain point in time t, individuals that are infectious are those that were infected at any time between 0 and the duration of their infectious period ago. Does it make sense? Yeah. Provided they survive, yes. If you want, we can have a chat about it later.
Yeah, in the Kermack-Kendrick model, which looks remarkably like.
Yeah.
You would,
Basically, yes.
Yeah,
which
basically
is, yeah, okay. You would, in the second equation, in your little box at the top, the one you started with,
yes.
you would have the integral of I of t dt. Or
Oh, I think the problem is that you can do a change of variable in the integral, and you end up with something that looks different but means the same thing while integrating on the other variable. We'll have a chat later about it. So calculating the equilibrium goes pretty much along the same line, with but now the element of the next generation matrix have to take into account this exponential term. Good. Okay. So the within host model, I need the within host model to decide what these functions are. Okay? So I have two choices. One is to assume that there is a competition between the virus and the immune system. This choice is possible, but usually there is no analytical solution for problems of this type, so it's going to be slow because you need to integrate it numerically. But in particular, there is no hope to have a simple system, very, very parsimonious, that gives me the infectivity profile of HIV, because it's bimodal. Okay, so the idea I took, well, the idea I exploited is to impose artificially the shape of the infectivity profile, decided from data, and instead change the frequencies of different types within the host. So the total number of strains of each type will be the total infectivity multiplied by the frequency of each strain at any point in time. This method is flexible, fast, but it requires some assumptions. And I would like to go through the assumptions, but they are a bit technical, and I'm not sure. Maybe I'll do it at the end if there is a bit of time, okay? But basically, the idea was to use the quasi-species equation because it has been formulated in many cases in evolutionary biology, and because it's studied quite a lot, so why not using this? And it is possible to use it, but you need to be a bit careful. I now describe the quasi-species equation. The quasi-species equation basically describes how different strains mutate and reproduce if they are allowed to grow unbounded. But instead of seeing the unbounded growth, we look at the frequencies of the strains. This is simply the linear system for the unbounded growth. So we have a vector that gives you the number of variants of strain I, with an associated vector where Gi is the reproduction rate of strain I. And then I have a matrix, Mij, that tells me what's the probability that a strain of type J, when reproducing, mutates into a strain of type I. So Mij times Gj gives me the reproduction mutation matrix, and I write the linear system. And this is unbounded growth. With the initial conditions, the solution is given by the exponential of the matrix. Okay? And now I need to look at frequencies. So I calculate the total population size at any point in time, and I define the frequencies of type I as the total number of individuals of variants of type I divided by the total number of variants. If I redo the calculations for this system here, but with frequencies, here I have a ratio of quantities that depend on time. If I do calculations correctly, I get something similar to before, but now there is a correction term that forces the vector vector x to add up to 1 at any point in time. And the solution, so the number of variants of strain, so the fraction of variants of strain I is given by the total number of strain I divided by the total number of strains. And if I plug in the solution from the unbounded growth, I get this result here. And these are the assumptions that are needed to make this system work, but I'll probably skip them now, and unless you're happy. If you have to go, you can go, of course. I'll probably come back to that in a second, well, towards the end of the talk, or to anyone who is interested. Now, of course, now we said that an individual is of type J if it's infected with strains of type J. So I need to look at what's the fraction of variants of strain of type I when an individual starts with 100% of strain J. And so as an initial point, as a starting point for my solution, instead of using any vector, I simply use a vector that has 1 at point J and 0 for any other element. In addition, to allow for more flexibility, I also have a constant here that tells me how likely it is for strain I to be transmitted between hosts. So there are some strains that can be transmitted between hosts more easily than others. So this is represented between host transmissibility. So my final function, beta ij of t, is given by a total infectivity profile, which is given, and it's calculated based on a set point vara load, which depends on the strain you got infected with, so strain J. Then the frequency of strain I at time t is given by the solution of the quasi-species equation, and then I multiply by a coefficient that tells me how good I is at being transmitted between hosts. Is it clear up to now? So fitness landscape. Now we needed to decide what these different strains are within the host. So we put an index to them from 1 to n, so we assume that strain 1 is the one with the lowest replicative capacity, and we assume that is 1 per day. So this is the reproduction rate of 1 per day. And instead, strain N is the one with the highest replicative capacity. Okay? And we vary this maximum replicative capacity from 1, so all of them have the same fitness within the host, to a maximum of 1.15. But for all this, most of the graphs I will show, I assume that the fittest strain is 2.5% more fit than the worst strain.
You have no evolution of new strains, right? You have
No, I have a fixed number of strains and they only mutate among them. Yeah. And then the between host transmissibility, I keep fixed the mean, and I assume that the different strains can have a different transmissibility, with a 5-fold difference between the best one and the crappiest one at doing that. And in particular, you can have a positive correlation, so the strain N is the fittest one within the host and also the best one at transmitting between hosts, or you can have a negative correlation where strain N is the worst one at transmitting between hosts.
And between host is independent of frequency, right? So if one strain is got a G of 2 but is half as frequent, and it's just as likely to establish.
Exactly. But the frequencies change over time according to the reproductive mutation. And then I have to choose some fitness landscapes. We play with three different landscapes. So we have a flat one where a strain can mutate into the strain immediately next to them in this list of strains, but they all have the same fitness. Or they can have a different fitness, and strain N can be fitter than the others, but still you can only move one step at a time. Or you can have, so this is the flat fitness landscape, this is a hill climb, and this is what we call the rugged fitness landscape. So you can jump from any strain to any other strain, but we assume that the fitness landscape has some valleys. So when you try to mutate, if you end up in a valley, you don't really appear in the population. And in order to jump to another reasonably fit strain, you have to harbor a double mutation in order to cross this valley in the fitness landscape.
So how is fitness defined again?
So the fitness, it would be the replicative capacity of the strain.
Within host.
Within host.
If it was there on its own.
Excuse me?
If it was there on its own.
No, it's basically...
They're all competing.
No, to me, it's basically the value of the G. So GI is the reproduction rate within the host. And to me, this is what I would call the fitness of the strain, of the within host fitness of the strain.
Attached to the strain, independent of which other strains are there, or
it is in itself. It is independent, but then they interact because you're looking at frequencies. If one strain is a lot faster than another strain at reproducing, it takes over very fast. And if it's a little bit faster, it takes over more slowly.
So relative growth rate.
So some results. Maybe it will become a bit clearer here. On a flat fitness landscape, if I'm infected with strain 1, I have 4 strains only. If I'm infected with strain 1, I start with 100% of strain 1, and then the frequency of strain 1 goes a little bit down because strain 2 comes in, and then strain 3, and then strain 4. Okay, if I start with strain 2, then strain 1 comes in, the blue, and also strain 3. They come soon. They come quite soon because they are all one step away from strain 2. Yes, they appear within the host because of mutation from strain 2. And so this is the flat fitness landscape. The hill climb, you start with strain 1, but then you immediately mutate into strain 2. I mean, strain 2 appears within the host and starts taking off, but then strain 3 takes over, the yellow one, and then strain 4 takes over and wins overall. But in order for strain 4 to take over the entire host, you need to traverse the fitness landscape, okay? Because you can only mutate one step at a time. If you start from strain 2, then strain 3 appears, and then strain 4, and strain 1 does not appear because it's less fit than strain 2. So any other strain is fitter than strain 1, so strain 1 does not take over at all. And if you start from strain 3, only strain 4 appears, and if you start from strain 4, nothing happens. And in a rugged fitness landscape, if you start from strain 1 or 2 or 3, then you need a double mutation for strain 4 to appear, but as soon as strain 4 appears, it takes over the population, and you don't need to traverse the fitness landscape because you can jump straight away to strain 4. But it will take over extremely fast because it's a lot, in this case, because his fitness or replicative capacity is a lot higher than that of strain 1. It's a bit higher than that of strain 2, is a tiny little higher than strain 3, so it takes a lot longer to invade if you start from strain 3. Okay? But of course, all these things will converge to an equilibrium which can be predicted for the within-host frequency of different strains. In this case, for example, in a flat fitness landscape, they all converge to a quarter of the strains because they are all equal. But what I'm interested in is not the equilibrium, but the transient dynamics at the beginning, because this is the infectivity profile of the individual. So it's only important to understand what happens until the individual dies. And this is the total infectivity profile of the individual. This is the asymptomatic stage. The acute phase goes over the top of the axis. And this is the constant infectivity during the AIDS stage. Note that this is in a log scale, because if you look at the linear scale, it looks pretty much like this. So this is the infectivity during the asymptomatic stage of an individual of type 1, which is very, very low, so you don't see anything what happens in here. This is the infectivity of strain 2, 3, and 4. So the log scale can be a bit deceptive, but it's there to allow you to understand.
I'm lost now, Lorenzo. How do you get the infectivity?
Sorry, which one? These infectivity profiles?
Yeah.
I get them from data. So this is the shape of the infectivity profile that I impose.
You're imposing.
Yeah. So in particular, I decided the duration of this phase and this phase are fixed. The infectivity of these two phases are fixed. And this one is decided by the set point viral load discussion I made at the beginning.
And those, I'm sorry, I've lost things as well. Those aren't related to the strain type.
Those are related to the infector strain. If you're infected with strain 1, you're an individual of type 1.
Even if that strain gets wiped out by strain 4.
Yes. Because it seems that the set point viral load of an individual is it's not necessarily completely determined, but data suggests that it's very likely that the infectious strain is descriptive of your set point viral load during your life. Data is very limited and very sparse, and it's not easy to conclude these things.
That's kind of critical. I mean,
it is
the link between this within and between those dynamics.
Up to a point.
That you're assuming this bit.
Up to a point. Yes, good point. But we tried also to have this infectivity here, this set point viral load that goes up, and you have a shorter infectious period with the modifications that occurred at any point in time given by the frequency of strains you have within the host. And the results are qualitatively similar. Or well, very similar, like almost identical. Does it answer your question? So basically, this shape, instead of being decided only by the strain you started from, is decided by the frequency composition of strains at any point in time. And the result is very similar.
I think I missed something too, but does it not depend at all on reinfection? I mean, this whole business about...
I know, but first of all, yes, I'm not assuming reinfection.
Exactly, and is that...
Well, it's not very clear from data what reinfection does.
Because just focusing on mutations after the first infection seems sort of odd, when in principle you could be infected by it.
Yeah, okay, I agree on that. It's a simplifying assumption. It's a very strong simplifying assumption. If you forget about that, you really have serious problems because you cannot use the multi-type models anymore. So the entire framework falls apart if you assume that thing. But you have to start somewhere.
Well, you have more than you have more types basically then.
Yeah, but how do you decide?
Well, you have to make some assumptions. You group your strains.
Yeah, you can.
That's exactly the problem with. That's exactly the reason why we don't have good within and between host mixed models.
Yeah.
Because that's
No, I agree. It's a limitation of the model.
To do.
Yeah. Okay. So if I have eight strains, as you can see, if you start on strain 1, you need to traverse the entire fitness landscape for strain 8 to appear. This is just to show that you can have more than 4 strains, but it's pretty much the same thing I did before. And this is for the rugged fitness landscape. Yeah. And now I look at the next generation matrix, and this is kind of key to understand what's happening. So this is the next generation matrix. I have 8 strains. Okay. So with a flat fitness landscape or very slow within host dynamics, then each strain mostly transmits itself. If you look at the picture here, basically throughout your infectious life, you are very likely to transmit the same strain you got infected with. And this means that the next generation matrix has large elements along the diagonal.
And your mutation rate is like approximately 1 per 1,000 or something.
My mutation rate is 5 times 10 to the minus 5. So each strain mostly transmits itself. The next generation matrix is strongly diagonally dominant, and at equilibrium, the strain with the highest transmission potential wins. So this is the next generation matrix. This is the number of individuals of type 1 infected by an individual of type 1. This is the number of individuals of type 2 infected by an individual of type 1. So if I sum all of them, I get the total number of cases generated by an individual of type 1, which is the transmission potential of type 1. So summing all the columns, I get all the transmission potentials, and strain 5 is the one with the, type 5 is the one with the highest transmission potential. So this is the distribution of transmission potentials, and the incidence at equilibrium is dominated by strain 5, by type 5.
Does it matter that there's zeros in K?
No, it basically means that an individual of type 7 does not generate an individual of type 1.
But you had a condition early on for the dominant eigenvalue thing working that it was all vectors are positive.
Yes, but it doesn't. That condition means that I can't split the matrix into 2 blocks that do not interact with each other. So that condition will be violated if I had a block where I have only elements here. It's a good point.
You just need all states communicating, not that every entry is positive.
Yes,
Yeah,
you need,
so
you need
some power
yes,
K is all
yes,
power.
you need states communicating from one. You need to be able to start from any type and arrive at any type.
Makes more sense to me than KIG is positive.
Yes, I know, but that's how it's technically
There are 2
described.
conditions, right?
Yeah.
There should be no negative, and you should go from any type to any other type in a number of steps.
Yeah.
Not necessarily direct.
Yes.
So most of the matrices that we, for any type of epidemiological or biological problem, are mostly irreducible, because you can usually do this.
Okay. So with a hill climb fitness landscape, then compared to before, so the transmission potentials remain identical. You just redistribute the number of cases a type generates among the other types. So instead of infecting, for example, an individual of type 2, instead of infecting 1.4 individuals of type 2, now infects only 0.7 individuals of type 2, because part of its infectivity goes into infecting individuals of type 8, because type 8 has taken over during the life of the individual in the within host dynamics. So can you see? Okay. So as you can see, the incidence at equilibrium gets shifted towards the right. And with a rugged fitness landscape, again, the strain that dominates here is shifted towards the right. In this case, it's individual 6. And because of how this fitness landscape is constructed, at equilibrium, we only have 1 strain instead of having a distribution of strains dominating. So if I assume there are no correlations, so the GIs, for example, the transmissibility between hosts are equal for all strains. All strains are equally good at being transmitted between hosts. In a flat fitness landscape, so this is what happens to the dynamics, and as you can see, if I start from only strain 1, then the other strains appear, and in particular, strain 5 dominates in the end with a certain proportion of strains of other types, and this is what you observe here. Strain 5 takes over, and the others are in other places. And in a hill climb scenario, you start from strain 1, strain 8 takes over because it has a very short life, so it takes over very quickly. But in the end, at equilibrium, what counts is the one with the highest transmission potential, which is strain 7. So there is something that happens during the initial phase, which depends on how fast different types come in and how short their life is. But in the end, the equilibrium is determined by the transmission potential of that strain. Or more exactly by the dominant eigenvector of the next generation matrix, which gives strain 7 as the top one. And for the ranked fitness landscape, you have a similar thing. Strain 1 disappears in favor of strain 8 in the transients, but then whatever wins is the strain 6.
So I'm now a bit confused what the type actually means.
So
You started with set point viral load, so I thought you were going to structure the population by set point viral load individual. But now we're back to strains.
No, I'm confusing how I say things. So when I say, okay, the type of an individual has type J if it's infected with strain J. That's why I confuse them. So if an individual is infected with strain J, it has type J, and the set point viral load for that individual is determined by the strain he got infected.
That sort of infection comes in,
Mm-hmm.
and it's only one strain that comes in.
Well, I assume that there are only individuals of type 1, so only individuals infected from strain 1. It might be more than one. It depends on the initial conditions of my system at the between host level. But they are all individuals of type 1, so all initially infected with strain 1. And then something evolves within them, other strains appear, they transmit other strains, so they create individuals of other types, and they start coming in the population. So these are types of individuals in a multi-type model.
Yes, they don't get infected by a quasi-species, they get infected by one strain, and that's your...
Yes.
Those you count collectively as the ones that were triggered by 1, that were triggered by 2, triggered by 3.
Exactly.
And all the other strains only appear after the infection takes place, right? Depending on the type of mutation.
Yes, so the infection is a bottleneck. At the moment in the infection, only one strain is transmitted, but the probability that you transmit a strain of at any type depends on the frequencies of strains of any type you have in your body at that time.
Yeah, but that's a very strong assumption, right?
Yes, that goes back to the slide I haven't described. But I'm happy to describe it to people who are interested, but I can't...
The biology behind that's quite strong. It's quite clear.
That you only get one strain in.
Yeah, that's the
most common number
theory, yeah. So there are some people who get multiple, but it seems the data so far is quite compelling to suggest that...
So you don't get a quasi-species in, you get, maybe it comes in, but you get triggered by one.
Yes.
And then the mutation starts from there.
That's the current, I mean, I don't understand all the details of the experimental method, but that is the very strong message.
Are the current data also quite clear in that there's a sort of progression a la influenza in the population that you know, so this would certainly restrict the type of mutations that you can, it's progressing, right? It's not...
Yes, it's a lot more complex than that, because...
But you had lots of pictures with many arrows that were possible, but in principle, it's not what you see, right?
What you see is a lot more complex, because you are infected with a certain strain, and the strain mutates in your body, generates other strains. You can transmit other strains to other people. They are selected according to a certain fitness within the host. If you transmit them to another person, and this other person has characteristics different from you, so that particular strain that it's transmitted to that person might be not really good in that person, so that mutates and might even mutate, reverting back to the strain you were infected from.
See, that's where my confusion comes from, why I asked about the fitness earlier, because you seem to define fitness as something that is separate from the individual, from the environment that this strain is in the individual with its history.
That is my assumption.
And that's a strong assumption.
I know, but I have to start somewhere.
No, I know, I realize, but it might be even a stronger assumption than not having reinfection, in which I think is you can get away with it.
No, it's a very good point. It's absolutely a good point.
It's not quite clear what fitness means here.
Oh yeah, okay. But in my case, fitness, and every strain has a fitness which is independent on the host they are in, and it's the reproductive rate of the linear growth that I described in the quasi-species equation.
Yeah, if there's nothing else in the host, and if you ignore, okay, so this, okay.
Okay? It's a good point, though. So, okay, so what happens if I look only at equilibrium, at the prevalence at equilibrium, which I can calculate, avoiding all the dynamics that I described here. I can go straight to the equilibrium. These figures are a bit complex, sorry. So you have 8 different strains, which determine 8 different types of individuals, from 1 to 8. Type 1 is infected with strain 1 that has a within host replicative capacity or within host fitness of 1. Strain 8 is the one that infects an individual of type 8 has a little g, a replicative capacity, which in this line is 1. So they all have the same replicative capacity. But here I study what happens if I increase the fitness, the within host fitness of the fittest strain according to these numbers, and all the others are linearly interspersed from 1, which is the fitness of strain 1, to the highest fitness, which is the fitness of strain 8, which is given by that number. Does it make sense? It's a bit complex, but
Is it a hill climb topology?
this is a hill climb and this is a rugged. And the flat fitness landscape is like a hill climb, but where all strains have the same replicative capacity. Okay? So, yeah, so in a flat fitness landscape, we know the strain 5, the individuals of type 5 are the ones that dominate the prevalence at the population level, because that's what you obtain from the next generation matrix. And as soon as you make the fittest strain a bit fitter, then you move to, then you start having some within host dynamics where strain 8 takes over. And the highest the fitness of strain 8, the more you're shifting this equilibrium to the right, because you're making the within host dynamics faster and faster, and strain 8 takes over over all other types. Okay? So if you change the value of the maximum replicative capacity of strain 8, you obtain different next generation matrices, and if you calculate R naught as a dominating value of these matrices, you see that for faster and faster within host dynamics, R naught goes down. This shows what I called the short-sighted evolution versus long-sighted evolution. If strain 8 is extremely fit and takes over the within host dynamics very, very quickly, this leads to a worse overall performance at the population level. The same thing happens with a rugged landscape, okay? But you have for any of these structures of the matrix, you only have one strain dominating at the equilibrium. But again, if you make the within host dynamics faster and faster, then the fittest strain, well, the equilibrium gets dominated by fitter and fitter strains over time, and yeah, and R naught goes down exactly as before. Here is by assuming that they are all equally transmissible between hosts. If the fittest strain is more likely to be transmitted between hosts, then the same situation as before is exacerbated. Okay. If instead I make the fittest strain the least transmissible between hosts, so there is negative correlation between them, then this distribution here is a bit shifted to the left, and then it's still, as soon as I increase the within host dynamics, it still tries to move to the right a bit, but then after a while the system kind of enters in a completely different state, where at equilibrium I have essentially only the strain 1 and a tiny bit of strain 8, which is a bit of a weird situation. So I was trying to understand what happens here. So this is the same picture with 16 strains, to show that you can do things with loads of strains, and it's not too difficult. But I wanted to examine what happens here in this, when you kind of seem to be switching regime from here to a slightly different thing. So if there is a negative correlation between the replicative capacity within the host and the transmissibility between hosts, this is what happens to the dynamics. And you start having what look like oscillations, which was a bit surprised about. So for quite a while I tried to prove maybe that there is no reason to look for an equilibrium, because you might have a limit cycle or something like this. And I really didn't manage to prove it, so I was a bit annoyed because the system is a bit too complex. And then it took me quite a bit of time to realize that it doesn't really matter, because it's a stochastic problem and my model is deterministic. And it's back to the Artofox phenomenon. It took me ages, even if I know about the thing, and even if I usually do stochastic models. So what happens is that basically you start with strain 1. Strain 1 generates a lot of individuals of strain 8 with something in the middle. They appear towards the end of the life of strain 1 because 1 is really not particularly infectious for a very long time during the asymptomatic stage and infects them during the AIDS stage. So they appear, they tend to infect themselves only, but their transmission potential is not enough to survive in the population. So they basically kill the entire population. So the prevalence goes to 0, and I should get extinction of the virus. But being a deterministic model, after a while, the susceptible population rebuilds and I have another outbreak. So beware of the limitations of deterministic models. So conclusions are, if there is an appreciable difference in the within-host fitness of strains, the within-host dynamics tend to be fast. Depending on the fitness landscape, the fittest strain seems to be winning all, or at least it drags the equilibrium peak towards higher set point viral load. In other cases, this is not what we see at a population level. If there is a positive correlation between within-host replicative capacity and between-host transmissibility, then the situation is exacerbated. For negative correlation, the situation is slightly relaxed for a bit, but you easily enter in a regime where the virus goes extinct. So we don't really know what's happening. Possible explanations: the within-host fitness range is not very wide, but data seems not to be suggesting that. And most likely the model lacks some important components. So up to now, what I'm saying is that there are two, at a population level, you have, data seems to suggest that you have evolved to maximize transmission potential. At the within-host level, data seems to suggest that the fittest strain wins all. These two levels cannot be easily reconciled. Even, I tried to model it, and the result is I still can't reconcile them. Maybe the model lacks some important components. For example, I assume that the immune system hits equally all strains, and this might not be the case. Might hit fitter strains harder. The fitness landscape is very difficult to traverse. So my toy examples were not complex enough. And no matter what happens in the host, maybe, and this is something important, maybe the initial strain are more likely to be transmitted no matter which other strains appear in the host. So there is some evidence that the strain you get infected with gets stored in the body, and no matter what happens within you tend to transmit that one anyway. And maybe a stochastic model might also make the results change a bit.
And you're looking at steady states.
I'm looking at steady states, yeah, but I'm also looking a bit at the dynamics, but not that much.
Well, but the main pictures and conclusions you draw from that are from steady state.
Yeah.
And that's not this, but the other
No, or this. No. It's really complex to follow the dynamics.
Can be more important than throwing in stochastics. It's
Probably, but the data, the population levels.
Yes, it should be stochastic, but
Yeah.
I'm not sure it would be better.
No, okay, but there might be some other things coming in the early stages that I haven't considered. So, thanks to the co-authors, and thank you for not falling asleep really during this long presentation. In particular, those that.
Dennis left for the Atterfox game.
I'm sorry.
He can watch it online.
Yeah. Thank you.
Have you thought about building in a latent cell class to get the carryover of the infecting strain effect?
Repeat it again?
So you know how Katrina has the model about the within and between host evolution?
Yeah.
And how they go through the various options and it comes out most likely that it's the early infecting strain goes into memory or storage and emerges and spreads?
Yeah.
So you could add a latent cell class that it's like yet another delay in your model so that it's impossible to work with.
No, not necessarily, but okay, if you have to extend this, this is definitely a sensible extension to try.
Yeah. So I was just wondering if that was on your radar as a near-term step.
Yes, among other things. But it's a good point. I mean, I'm collaborating with Katrina, so I think that point will be made by her. Any point?
somehow it seems to me that you have at least two different phenomena, or three maybe even, that you want to look at simultaneously.
Yeah.
There's this stuff about the importance of the early infection versus the late infection,
Yeah.
which would play differently in the beginning of the epidemic and in the middle of the when the epidemic has reached endemic equilibrium.
Yeah.
So that's one thing. The next thing is this question of the relationship between within fitness and within the host fitness and among, from one host to another fitness.
Mm-hmm.
How did you do the last one?
Okay, there is not much data about how likely different strains are to be transmitted between hosts. So it's purely speculative at that point. The only way I could find was like adding a coefficient, an overall coefficient here. So this would be, this is the total number of variants you have in your body. This is the frequency of strain I. So this is the total number of variants of strain I, and then I multiply it by a coefficient that tells us how likely I is to be transmitted. That's the simplest way I can think of. So this might represent, for example, an overall parameter to tell how likely it is for strain I to survive outside the host, or how easy it is to just get into hosts, get into a host once it's in the air. So some strains might, I don't know, I really have no idea about the biology, but it seems sensible to assume one parameter. Good. I think you should be left free.